The sides for that, let's see, I started recording. Hopefully everyone can hear me okay, virtually and in person. So, okay, let's go ahead and get started. So we were talking about, last time we were talking about really radians. We started talking about radians. And in particular, just pretty much a quick synopsis on radians. Radians are another way of measuring degrees, or measuring angles. One way we measured angles was in degrees, but quantitatively, angles, degrees are not normally good at being applied to other values. We use radians as a way, so in one sense, you can view a radian as the fraction that represents a way of partitioning various distance around the unit circle, as I have illustrated here. So the pi over 2, the underlying fraction is 1/2, and that represents 1/2 of a distance from the positive x-axis to the negative x-axis, and you can go on from there. And so, yeah, also yesterday we were talking about how to convert. I have the two formulas here. I also decided for the midterm I am going to give a few formulas, including law of sines and cosines, so you're welcome. So I'm going to provide those formulas, maybe one or two more, I don't know yet. Definitely law of sines and cosines, so that will be available. And so, yeah, so all these conversions here, we did those yesterday, and we talked about how to convert the special angles, because as we go on through this class, in the next chapter in particular, we're going to look at things from more of a radian perspective, but knowing how they associate to their degree representation might give you a more intuitive idea of how to connect it to, say, the special triangles that we talked about. But in the meantime, let's go ahead and we're going to go ahead and step these up a notch. So before we were converting from radians to degrees or degrees to radians, and now we're actually going to find function values. So it's find tangent of this radian measure, sine of this radian measure, cosine of this radian measure, and just go from there and see how standard problems like this would go. And normally what I recommend, or the way I'd like to start talking about this, the 2 pi over 3 for the first problem. Oops. Okay, this might be off a little bit. The calibration's not right, so it might go in and out. I might have to erase a few times. Okay, yeah, that's kind of weird. I'll have to get used to it. 2 pi over 3, I'm going to go ahead and convert this to degrees, because we have a more intuitive understanding of degrees. So if we take the 2 pi over 3, we're not even looking at tangent yet. We need to figure out how to convert radians to degrees. And the way you do that, normally the way I think about it, is you divide out the pi, and then you multiply by 180. And so by doing it this way, you'll notice that the pi's cancel. And then we're left with 2 over 3 times 180, which is probably 12 or something. Or 120 rather. No. What's that? It's 120? Cool. So that is 120 degrees. We didn't even touch tangent. So all we did was we have now changed the problem from tangent of 2 pi over 3 to tangent of 120 degrees. And so now it becomes a problem that we've looked at in the very beginning of this section. So how did we figure out tangent of 120 degrees? Well, we figured out where 120 degrees belonged on an XY plane. So 120 degrees, this would be 90. A little bit further to get 120, because too far and we'd hit 180. Then hopefully it should be familiar from here what to do. So we triangulate. So same stuff as before. It's just all we did was start off with radians, and we convert that to degrees, and then everything else follows the same. So this should be mostly review. So when some of you have asked me, is the midterm cumulative based off of what we've learned so far? My answer is it's naturally cumulative. Just it's going to focus more on the material after the first test, but math is a naturally cumulative topic. We tend to base new things off of old things. It's kind of hard to avoid dipping into topics from previous sections. But in any case, that means we should probably figure out that reference angle, which hopefully you remember how to find reference angles. So the reference angle of 120 is just 60. Because you already went 120 of the distance. What remainder of the distance would bring you all the way to the negative x-axis to give you 180 in total. That's 60. So we do have a triangle that we've formed, which I'll put over here. So this is a 30-60 triangle, and hopefully you all remember how the segments of a 30-60 triangle are filled in. Across from 60 is the square root of 3. Adjacent of 60 is 1, and the hypotenuse is 2, with one exception. What's the exception?
-1.
It's -1. It's -1, because we went to the left. So we have to throw that part in there. Oops. And then from here, we just find really, so really the triangle will help us find tangent of 120 by looking at the tangent of the interior angle here. So tangent here, so what's tangent in general? It's opposite over adjacent. Opposite seems to be square root of 3. Adjacent seems to be -1. So our final answer, because we can simplify that pretty quickly, this is exactly it. And that would be the answer. So the majority of this is stuff we've looked at before. I feel like there was a homework where I graded where a lot of you forgot the signs on tangent of, could have even been 120. It was something like that, and a lot of you forgot that 1 needed to be negative. So going back on that point, actually, tangent of 120 is not equal to tangent of 60, which I saw a few of you. Actually, it was on the last test, that unit 1 test that we had. There was a lot of you that made this association. The reference angle is not an equivalence. It's a shorthand that allows us to look at things in a more simplistic format, but you can't forget about those signs. That's what I'm trying to say. In other words, the thing with reference angles is you have to remember these signs, like -1. But that's really all I have for this problem. Does anyone have any questions? All right, let's fix this. This is driving me crazy. So just hang tight. That's a little better. Okay, sorry about that. All right, let's move on to problem 2. Problem 2, it's sine of 3 pi over 2. First thing we're going to do is convert 3 pi over 2. We're going to convert that to degrees. And same thing as before, the way you convert from radians to degrees, you multiply the quantity by 180 divided by pi. Again, it's good to think about this. The intuitive way of thinking about this is that the pi's cancel, which is also good because putting pi in your calculator will normally give you some weird decimals. But 3 over 2 times 180, is that 270? Yeah. 270, cool. Degrees. And from here, so really the problem we have now that's all we've really done. So now the idea is the same as before. We need to figure out how much 270 is, which, that's a good question. 270, that looks kind of familiar. It is a quadrental. It's a quadrental because 90, 80, 270. And I'll use blue to really emphasize it here, but it's a quadrental. 3 pi over 2, or 270 degrees, that's a quadrental angle, which means that the terminal side lies on one of the axes, as it does here, as I illustrated in blue. Because of this, we can't make a triangle. So we can't use the triangle, which means we have to use the quadrental specific method of determining, well, sine of 270. Well, Blake, you seem to be on a roll. What is the quadrental specific method?
You find a point on one side.
Yeah, we do find a point. Or just find any point. And what would be a, let's see, what's a good point that would make sense to go there?
0 and -1.
Yeah, 0, -1. That would be a point that would make sense right there. And from here, we found an x, we found a y, we also need an r. Yeah, that's where the Pythagorean theorem is going to come into play. So r, remember r is the square root of 0 squared plus 1 squared, or -1 squared. It doesn't really matter because you get 1. And r is always going to be positive because square root always outputs a positive. And so from here, it's just a matter of remembering the formula. So sine of 270 degrees. So opposite, adjacent, and hypotenuse are out the window because we don't have a triangle. So we have to remember those general formulas. So sine is y divided by r. That was the general formula for sine. So it is y for sine and not x. It's y for sine. So it's just a matter of filling in. -1 for y divided by +1 for r. Just get -1. There was a question on the Unit 1 assessment that asked you to find, it could have been written in one of two ways. The way that comes to me is cotangent of -90 degrees. It said do not use the calculator because the calculator will lie to you. And so how do you find the cotangent of -90 degrees? It's almost exactly the same way you find sine of 270 degrees here. You have to pick the point and determine it as such. I think about half of you did not get that problem correct on the test. And you would use this exact method to find it. Okay. Any questions? Should I keep going? So let's do that. Cosine of -4 pi over 3. First thing I'm going to do. Nothing new here. I'm going to convert the radian into degrees, just so we can have a better intuition about what the angle will look like. So pi's cancel. 4 pi over 3, -240. 18 divided by 3, 6. 6 times 4. Is it -240?
Yeah.
-240 degrees. So now what we have is cosine of -240 degrees. So we just pretty much rewrote the problem. But there's a, perhaps not a domain issue, but there's kind of an annoying aspect of how the problem's set up right now.
It's negative.
It's negative, which generally, from my experience, people don't really handle the negative sign too well. So we're going to find something coterminal to -240. So hopefully you all remember what the word coterminal refers to. So we're going to add 360 because we're going to find a positive coterminal angle to replace this with. Let's just get 120 again. It's kind of boring. We just had 120. Oh well, we get 120 again. Well, at that rate, we can pretty much recycle the diagram we had from the first example because we had 120 degrees before. We're going to do it again. So the diagram we had before, we had a special triangle. We're going to use the triangle from part 1 because we already did 120 degrees, so I don't feel like doing it again. You would set it up the same exact way. You would get 60 as the reference angle. You would get square root of 3 and then -1 and 2. You would get the same exact triangle. It's the same exact process. The only difference is it's Now we're looking for cosine of 120 instead of tangent of 120. So the triangle is the same, just that cosine of 120. Well, hopefully you remember what cosine is. That's adjacent over hypotenuse. Adjacent is -1, the hypotenuse is 2, and we have an answer. Does anyone have any questions about this? If not, that concludes radians, brief introduction to radians. And this homework, probably get it to me by Friday at midnight. Friday at, well, I guess I should be technical. Friday at 11:59 p.m.
Is this homework we're about to do, is it gonna be with it,
The homework you're about to do.
or for 4.2, the next section?
Yeah, that's going to be concurrent with it. So, in other words, I'm going to have 4.1 and 4.2. Both of those due on Friday. So, which a lot of them are going to be convert this, convert that. A little boring, but in fact, I might take off some of these. I don't know yet. If I send out an email, I'll just send out an email to say, hey, there's a lot of redundancy here. Let's not do as many problems. For now, it stays. But so Friday at 11:59 p.m. That's when 4.1 and 4.2 will be due. And just to emphasize, keep in mind this is 3.1 in the book, and the next section is 3.2 in the book. So radian measure is 3.1 in the book. .2 is 3.2 in the book, which we'll get to momentarily. Cool. Any questions for me before we move on to the last section before the midterm? Because if not, let's do exactly that. Applications of radian measure. So, of course, as I mentioned before, there is a reason why we like radian measure over degrees for angles. And one of the reasons is that quantitatively, radians give us more arithmetic exploration. And that is true with application problems. The natural immediate application of all of this stuff is these various word problems that could be engineering, mainly engineering based. Engineers use trigonometry a lot. So we start off with something called the arc length. So we start off with the arc length. And the arc length, well, this diagram, I have this diagram drawn out right here, which explains what the arc length is. The arc length is how you measure, well, an arc. So if you wanted to know what the measurement of this arc was, or in other words, if you took some arc and you flattened it out to make it completely flat, then what would that length be? This formula does exactly that for you. The formula in particular, it's S is equal to R times theta, where S is, well, the arc length. That's their notation for it. R is the radius, the distance from the origin to, well, your circle, the end of your circle. And theta being the angle in radians. So This is the first time we've seen an angle just by itself. Normally, every theta or every angle is generally accompanied by a trig function when we use anything arithmetic involving it. I mean, this isn't the case for if we're adding angles or subtracting angles, but normally we don't multiply by 60 degrees. Normally we multiply by, like, say, sine of 60 degrees. Here, it's interesting that theta is by itself, and because of that, we want to utilize the radian form to really get a congruent answer from this quantitatively. So it's very helpful, and it's actually pretty easy to apply. So it says, for example, 1, refer to the figure. I did not draw a figure. I was trying to figure out how to type it, and I was getting frustrated and gave up. So I'm just going to draw it here. So the figure in question, it's a circle. And what this is, it's a pulley system that has a weight connected to it. So that's a weight. And I know there's one value I have to provide, which I have here. Where is it? Where is it? 9.27 for the radius. 9.27 inches. So 9.27 inches. So it's a pulley system. It's this, think about it as, just a wheel, and it's got a weight attached to a rope. And simply all it does is, well, as a pulley does, as it rotates, the weight will simply go up or down. That's really pretty much it. So you can think about this as starting position. And then part A, it says how many inches will the weight rise? And they give us the rotation of the wheel. So really what we are envisioning here is they are telling us the rotation being 71 degrees and 50 inches. So they're telling us the rotation is 71 degrees and 50 inches. We know that the distance from the center of the wheel to the edge of the wheel itself is 9.27 still. And really what we're trying to find, so think about it as the weight has now gone up in distance a little bit because the wheel has rotated, which has pulled the weight up. And so we want to figure out that distance. So in other words, what we're trying to find is this arc length here. Because that tells the distance from the starting position to where the rotation has pulled it to. So I'll call that X. I don't know what it is. So the formula itself is S is equal to R times theta. So the main mistake people make is that they will write, in fact, I'll do this in red because this is what you don't want to do. So, all right, the radius is 9.27. We multiply that by the angle, which is 71 degrees, 50 minutes, and you're already wrong. You already did that. It's incorrect. The reason why you do not use degrees. You use radians. You have to use radians in this problem. The formula makes you use radians. Quantitatively, it's the same reason why we don't use the percent quantity when if we try to figure out 20% of something. We don't multiply by 20, the quantity of 20, we multiply by 0.2. And this is the same idea, so we have to convert this. So off to the side, 71 degrees, 50 minutes has to be converted to radians. So hopefully you remember how to do that. It's pi divided by 180 degrees. And the interesting thing here, you're probably wondering, do I need to keep an exact answer? And really with application problems, the answer is no. You don't need exact answers for application problems. Decimals are perfectly fine. So let's just make sure we can type this darn thing into the calculator correctly. So 71 degrees, 50 minutes times pi divided by 180 degrees. And I'll call it 1.254. Did other people also get that? Okay, cool. So this is the radian value. So it would be read as 1.254 radians. And you can convert to decimals when we have, well, an application problem that does not ask for an exact value. So now we have the radian value. So this is kind of work off to the side. We did that. And now we can come back to our formula, which says that the radius is 9.27. The theta value, it's the radian value, which we found to be 1.254. 1.254 times 9.27. I'll call it 11.6. Why not? And this was in inches, so I guess I'll be consistent. But that would be the answer. No idea why my notes have spacing for B, but on here there's no spacing for part B. There's no space to put the problem. I did not put any space here, but in my notes I have plenty of space. It's interesting. All right. Well, what I want to do about that is, one second. All right. One second. Wait a second. You'll just hang tight. You might have it.
Are you sure that wasn't witchcraft?
It's just need to figure out where I put the darn thing now. See, this is why you should not use a Windows computer. You should just stick to Linux. That fix it. Oh, there it is. I guess this is good because I'm trying to waste some time. And it didn't work. Okay, I never updated it. Interesting. All right, that was a big waste of time. Fantastic. But if anyone's interested in learning about computer science, let me know. We can do some cool stuff. So what I'm going to do here, since I didn't put any space, I'm just going to open up one of these things and do it here. All right. So the problem, hopefully you all have your notes in front of you. So remember, the original diagram was a circle. It was 9.27, and there was a weight that came down. And then for part B, what angle to the nearest minute? Raising, so part B, I'm just going to paraphrase. Raising the weight 6 inches. What is the angle? That's what it's asking. And it does say to the nearest minute, so I'll keep that in mind at the end. Or I might forget, you all have to remind me. So this is independent of part A, so we're not going to use any of the results from part A. So part B here, the diagram we are looking at. They're already telling us the arc length. They tell us this part. They want us to find the angle, and we already know the radius. So remember, the formula is S is equal to R times theta. We don't have to convert anything right now because we don't know theta. We don't even know theta in order to convert it in the first place. So they actually gave us the arc length is 6. We know the radius is 9.27. And now we don't know theta. That's what we have to figure out. And so the algebra here is really quick. And I'll convert it. Actually, all right, I have it in the calculator. I'm just going to write out a few digits here to make sure we all got the same thing. But I'm going to keep this up in my calculator because what we found is an angle in radians. This formula will only give us angles in radians. So I'll put rads for radians. And so from here, the problem wanted to know what is the degree value in minutes. This is not a degree value. This is a radian value. So in order to convert to degrees, really, I'm going to take the full value in my calculator. I'm just writing the 0.647, make sure we're all in the same boat, but I'm going to take that whole value. So how do you convert from radians to degrees? You multiply by 180 divided by pi. And then you should get something along the lines of 37.08. This is a decimal degree. This isn't degrees, minutes, seconds. They wanted one more step and they wanted the final answer in degrees, minutes, and seconds. Oops, sorry. Hide, extend, okay. So this is in decimal degrees. So finally, if we convert to degrees, minutes, seconds, it's set to the nearest minute. So the nearest minute, so it would be precisely 37 degrees and 5 minutes. And if you're off by a minute,
So when I put 0.647, I just did answer DMS on my calculator. It gives you 0 degrees, 38 minutes, and
well,
0.5.
well, you said you
So-
found the degree version, the degree minute second for 0.647.
Yes.
Well, that's not a degree. That's a radian. So here, so
Finding it
Fine for
37.
37.
Yes.
yeah, then once you convert to 37, you get decimal degrees, which then you convert to DMS.
I got like 37 degrees, 4 minutes, and 12 seconds. So do you just go up automatically?
Well, I kept all the exact answers in my calculator, and I just did ANS, ANS, ANS. So really, I did ANS times 180 over pi, and then ANS converted to through DMS. I just feel like I'm throwing out a bunch of numbers, or a bunch of letters rather, but hopefully you're up to speed. But it might be off by a minute. Who cares? As long as I could see your process. Like if I asked this on a test and you got 37 degrees in 3 minutes, but you did all the steps right, I don't mind that much. That's not a big deal. That's close enough for me. But that's part B. Any questions about this one? Why is the spacing like that? That's so weird. All this extra space down here. Well, there's no other questions. Again, part B is over here. So let's move on to example 2. So 2 cities. I don't know if anyone's ever visited Charleston, South Carolina. It's a pretty cool city. Toronto, I bet it's cool. I don't know much about that one, but these 2 cities are 1,100 kilometers apart, and they lie on the same north-south line. So if anything, to put all of that into perspective, there's a globe. So let's think of this as the equator. And it says 33 degrees north of that equator. It's going to be where Charleston's at. And then if you go up a little bit higher, that'll be where Toronto is at. And so I'm getting distracted because I realized I just drew kind of a face. Not a very good face by any means, but so the information that they gave us, they told us that the difference between these two, I'll use blue for this, the distance between these two is 1,100 kilometers. That's what they told us. And they also tell us that the latitude of Charleston is 33 degrees north. So Charleston was the first one. This one, that's Charleston. Of course, the other one's Toronto. They told us, really, they're telling us the angle here. The angle here, they say, is 33 degrees. And north just meaning it goes up instead of down. So they've told us all this information. And finally, what they want us to find is the full angle of latitude for Toronto. So what I have in purple. We're looking for what's in purple. So we're given all of these, really these fragments of information here, it seems like. And now we need to put all of this together in some way. And there's one bit of information. I don't know why I left it off. I think it's 64. Okay. There's also, this should be part of the problem. Radius of Earth is 6,400 kilometers. That should be part of the problem. So that's assumed. You're just given that as well. So they're giving you the radius, in other words. So we have quite a bit of information here. So the issue, so remember, we're looking for this purple arc right here. That's ultimately what we're looking for. That corresponds to the latitude of Toronto. The problem is we can't find that arc because we don't know, in order to use the formula, we need to know this whole segment right here, that whole segment. But we don't know that. So what I'm going to do is determine first the distance from the equator to Charleston. So I'm going to figure out this distance right here. I'm going to figure out that distance in red. So really, I'm just taking out that, basically think about it as a pie. I'm taking out that little slither. So none of this has anything to do with Toronto. We're just ignoring that one for now. This is all relating to South Carolina, the Charleston, South Carolina, which means I'm putting S for the whatever it's called. What's that?
Arc length.
Yeah, it's the arc length. I just completely forgot that. Yeah, that's the arc length, yes. So here, we can't use this 33 degrees. We can't use the 33 degrees because arc length requires radians. So we have to convert 33 degrees to radians, which means we have to multiply by pi over 180 degrees. And this is another application problem. We can go ahead and just figure out the decimal version. And you should get something that looks like 0.5, call it 576. Good enough. And so now the arc length is r times theta The radius is 6,400, which was given to us, times 0.576. That's 3,686.4 kilometers. So we found the arc length, which is a length. It's not a degree, it's a length. So this first quantity, what this first quantity represents is the distance from the equator relative to the same north-south line to Charleston only. And now, to figure out the full arc length, which will ultimately help us figure out the full angle, well, we figured out the arc length here just now, and we're given this one as 1,100 kilometers. We just add the two together. So we're adding the two arc lengths together. This gives us the total arc length. So this actually tells us the distance from the equator on the same north-south line to Toronto. It gives us that whole entire arc length. Because originally the 1,100 was only the distance from Charleston to Toronto. But now that we have the whole arc length, now we can find the whole angle. So step 2 here. The whole arc length is equal to the radius. I should probably write a little bit smaller here. The arc length is equal to the radius times, well, the final latitude that we are looking for. So really all we have to do is divide. Call it 748. Why not? And this is radians. We're going to go ahead and view this in degrees. So how do we convert this to degrees? I'm going to multiply that by 180 divided by pi. And that would be our final answer. There's a homework question that's very similar to this, so hopefully you can recreate those steps. Does anyone have any questions? Yes.
We need to, if it's dealing with direction, we need to put north to it or anything, or will you take that as?
This answer's fine. Yeah, you could put north next to it just to be consistent. Without the north, I'm okay without it. I think there was a few questions on the test where, actually, I'm confusing two tests, never mind. I'm normally not too picky on having the units there versus not having there. It's pretty lousy nitpick. I don't care that much. Okay, well, let's move on to one last problem. And this is how to find the area of a sector, which is just a slight step up from what we had before. The area of a sector, well, We have a formula here, which notice that we have similar variables coming back into play. The radius and the angle in radians again. So again, the angle has to be in radians and not degrees for this to work. And so what you're doing, instead of finding the arc length, so the diagram down here, instead of finding the arc length, we're finding the area generated by everything enclosed within that angle. So we're finding, of course, everything shaded here. So that's just, we're finding that area. And so that brings us to example 3, which says find the measure of a central angle. Well, really just the interior angle, in other words. And they tell us the area. They tell us the area and they tell us the radius. So really, we are taking the formula from above. So write it right here. They tell us the area already. They tell us the radius. We're going to find the angle, theta. Really, 1/2 times 3 squared. 3 squared is 9. 9 times 1/2 should be 4.5. Cool. And then from there, all we have to do is one more thing. And 2 decimal places, that's fine.
Fifth degrees.
What's that?
Fifth degrees. We're gonna have to convert it to radians.
Well, there's an even worse problem. There's a worse problem here. This isn't a degree at all. It's not a degree. It gives you a radians. Yeah, it gives you radians. Yeah, it gives you radians. So how do we convert? Well, we don't have to. So, I don't know, very tricky to compensate for the fact that this is not a very exciting problem, but hopefully it'll keep you on your toes as you do the homework problems. And that is it. Because after that, it's the stuff after the midterm. So, really all I have. So I guess while I have all of you here, the midterm is going to be a week from today. So it's going to be in class because I did not get any notification from anybody otherwise saying they have to take it remotely. So I'm anticipating everyone's going to show up a week from today, take a paper test, which will be the duration of the class, and I'll give you some formulas. If anything, I'll give you the sine and cosine formulas on the test. I'll think about the other ones as well. But I'll talk more about it on Thursday's session. So Thursday's just going to be a review session. We can talk about any homework problems as well for Thursday, since the homework's due Friday at midnight, so 11:59 technically. So that's really all I have. If you have any questions, I'll stick around. Other than that, have a good day.